Ben bir mühendisim. Ofiste, evde, yaşamın her alanındayım. Görülmeyen ama hissedilenim. Ben ne kadar görünmez olursam, projelerim o kadar başarıyla tasarlanmış ve uygulanmış demektir. Tıpkı sizi sizden fazla düşünen gizli bir kahraman gibi. Kahramanlık, kağıtla kalem bir araya geldiğinde geleceğe yön verebilecek kadar cesur olmaktır. Çünkü mühendislik, bilim ve doğa alanında tüm bilinenleri yine doğa ve insanlık için kullanmaktır. Tasarımda sadece estetiğin değil, sürdürülebilirlik, enerji verimliliği, çevre duyarlılığı gibi kavramların da altını çizmektir. Mühendislik, modern, konforlu ve doğaya saygı gösteren yenilikçi yaşam alanlarını hayal etmek ve gerçeğe dönüştürmektir. Gelecek kuşaklara yön vermektir. Binlerce yıl önce bir kıvılcımla yaratılan aydınlığı bugün tek bir tuşla milyonlarca insanın yaşadığı yerlere taşımaktır. Geceyi gündüze, soğuğu sıcağa, sıcağı soğuğa çevirebilmektir. İnsanlığın ihtiyaçlarını karşılamak için hayallerimizi gerçekleştirirken yanımızda TTMD vardı. 1992 yılında kurulduğundan bu yana çatısı altında güven bulduğumuz, etik değerlerin teşkili ve temel sorunların çözümü için birlikte çalıştığımız yol arkadaşımız. Farklı disiplinlerden gelen profesyonellerin ortak amaçlar için toplandığı TTMD, üyeler arasında iletişim ve tartışma ortamı yaratıyor, bilimsel ve teknolojik yayınlar yapıyor, üniversite, sanayi, işbirliğine destek veriyor, çevreci ve enerji verimli çözümlerin yaygınlaşmasını destekliyor, yurt dışındaki gelişmeleri izliyor ve sektörü yurt dışında temsil ediyor. Bizler tüm insanlığın iyi yaşam arayışına çözüm buluyoruz. Bizler yarınlarımızı şimdiden kuruyor ve daha sürdürülebilir bir dünya için çalışıyoruz. TTMD, 1992'den bugüne yaşam mekanlarında insanlığın konfor ihtiyaçlarını doğaya saygı göstererek sağlamak için var. Mühendislik mesleğini etik değerler doğrultusunda uygulamak için var. Türk Tesisat Mühendisleri Derneği. Gelin geleceği birlikte yaratalım.
Hello everyone. Today we will have our webinar on building energy performance modeling and simulation. The speaker will be Professor Joe Clarke. I want to thank him again here because against all of the negative incidents, he is here today with us, and he's going to share his experience with us. I'm very excited about that, and I hope it will be very useful for us. Now I would like to introduce myself. I'm Neşe Ganiç Sağlam. I'm an assistant professor in Özyeğin University, Faculty of Architecture and Design. I'm an architect. I am the board member of IBIFSA Turkey, International Building Performance and Simulation Association, and we have the Turkish affiliation of that, and I'm the board member of that affiliation. And I will also introduce Professor Joe Clarke. Most of you probably know him. He is emeritus professor at the University of Strathclyde in Glasgow, where he had a leadership role in establishing undergraduate, postgraduate, professional development course in the built environment. He's a founding member and past president of IBIPSA. He established the Energy Systems Research Unit in 1987 as a means to enable cross-discipline research in the field and incorporate outcomes within open-source modeling tools for use by practitioners. His observations today derive from his experiences in this regard. Now, I would like to give the stage to him to share his valuable experience with us. Professor, please.
Tell me, Neşe, can you see my screen?
Yes, we can see the screen.
Okay. So, good afternoon, everyone. It's a pleasure and a privilege to be with you today. I first experienced the delights of Turkey in 1986 when I was a visiting researcher at TÜBİTAK in Ankara. 1986 was the year of the first ever IBIPSA conference. So that's basically the birth year of IBIPSA. And that was the year I first visited Turkey. The purpose of my visit then was to discuss what was emerging at the time in terms of building performance simulation. Today, I would like to share with you my personal experiences on how this technology has evolved since then. These observations are directed to practitioners in the audience who might want to embed performance simulation in their business. I direct my observations to researchers in the audience who might want to evolve the state of the art going forward. And I direct my observations to academics who will train the next generation of modelers. So, this is my first observation. We're no longer concerned with building performance simulation, but rather buildings in the context of all what's happening in terms of the clean energy transition that is now underway. So the target of our simulation programs has expanded dramatically since 1986 to include probably not one building, but several communities, the energy grids that connect these, and the myriad energy systems that service these buildings, from local embedded systems to more national strategic level systems. So that the nature of the target is much expanded. And this situation has increased the complexity when we try to author computational tools to help practitioners. Let me just explain that a little more so everyone's on the same page. So on the demand side, we have so many conflicting options on the demand side. What I've done here is to, give me a second, to organize these into three categories. Those some demand side options that relate to design features, switchable glazings, ventilation preheat using solar energy, adaptive facades, evaporative cooling, phase change materials. So there's lots of industries representing these notions. Then there's the heat-related demand-side options. Obviously, the big one coming up is heat pumps, but there's many others, and we'll probably see hydrogen systems in not too distant future. And then there's all the electricity-related demand-side options, as listed here: integrated PV, smart technologies, fuel cells, combined heat and power. And there's different parts of the industry promoting different mixes of these demand-side options. Some of them are mutually exclusive. If we deploy some of these options. That then means we cannot deploy other options. Some of them are mutually reinforcing, that if we deploy two together, we get more out than the sum of the parts. So performance simulation has to address this complexity on the demand side, and it therefore has to evolve to facilitate multivariate appraisals, where we can look at effective solutions which derive from appropriate blends of these things which suit the context of our design. If we try to use simplified design tools for this task, they are totally inappropriate. They will get the wrong answer, they will send us in the wrong direction. Also, if we try to use just a legislative approach, a tick box approach, you get so many points for smart meters and so many points for a condensing boiler. That doesn't realize good solutions, effective solutions. What we need to move towards is being able to simulate the proposal in terms of all the interactions that are taking place, and then judge the outcome against what we're trying to achieve in terms of comfort, air quality, emissions, energy use, and so on. So here on the supply side, we have equally many conflicting options. We've got fossil fuels, which have to be carefully managed in the decades to come. They have to be used wisely. They have to be used in a way which is more acceptable to the policy directives we have to follow. We've got new nuclear coming back, and that gives us a completely different load matching capability. We've got the strategic renewables, whether it's solar or biofuels or wind, and they give an entirely different stochastic low power density capability that has to be matched. Then we've got future strategic renewables in some parts of the world, particularly where I live in Scotland, wave and marine tidal stream. I just need to keep bringing a pointer. So we've got the strategic renewables, and they will come on slowly with a small contribution over the coming years. And when we try to decide what level of offshore wind, what level of tidal stream, what level of wave, what level of the strategic renewables that exist at present, how do we mix them with the more baseload type plant? Then there are ideas for urban renewables, whether that is biomass, whether it is heat pumps, integrated PV, district heating, but in the cities, the geothermal in the cities, that needs to be considered. And then we've got emerging slowly, but nevertheless, very, very importantly, energy storage technologies. And so our solutions need to take account of the complexity in the demand side and how we might mix some of these supply side options to match supply and demand. So performance simulation has to evolve to address the temporal match, the match across time between supply and demand at different scales, the individual building, the community, the district, the city, the country. And that's the target that the simulation has to address. And when we look at these options in demand and supply and start to mix them, we find there's all sorts of conflicts emerge. If we're trying to go for electrification of heat, which many countries are, which governments are pushing net zero energy or net zero CO2, and that gives rise to a whole set of other conflicts which may be compatible with some of the other system options. People pushing forward on smart grid services. District heating is still big business. smart districts where everything's coordinated, embedding all these renewables in our buildings. These are ducted wind turbines and PV facades. And mixing all of these technologies, combined heat and power, heat pumps, biomass boilers, PV, fuel cells, ducted wind turbines, energy storage, as we reshape demand. And then we've got electric vehicles coming on, which are going to be an integral part of the built environment. And the table down here are all the things that we're trying to do. We're trying to reduce costs. We're trying to make sure there's occupant well-being. We're trying to make sure we don't make fuel poverty worse. We're trying to make sure that air quality doesn't suffer. We've got to operate hybrid systems, which is a control system challenge, and so on. We've got to make sure as we go for these kinds of systems, the communications are resilient, because I've seen lots of projects fail when the communications fall and they can't operate the system. We're going to move towards real-time transactions. So the simulation models have to be able to emulate real-time control and transactional control. And of course, as the technology comes on, we're going to have to take account of, when we're looking at systems like this, policy conflicts. Some of these systems will give rise to some aspects of policy, but not others. Might exacerbate cost in terms of maintenance cost, for example, whilst perhaps including improving environmental emissions. So there's a policy conflict. And we have to change our work practices, perhaps, because it's not about calculating things. It's about making models that are properly formed, properly tested, properly simulated, and properly analysed. And that's a whole change to company work practice. And we also have to take account of uncertainties and risk, which abound, they're everywhere. So performance simulation is evolving and needs to evolve further to enable whole system multivariable or multivariate appraisal under realistic operational scenarios. We're not trying to predict the future, we're trying to emulate reality, so that when we emulate our design, we can say that's got a very good chance of performing the way we expect in practice. We're not trying to predict if we'll overheat 3 years from now or what the energy cost will be 2 years from now. We're simply trying to emulate the reality to get the robustness we need and the resilience we need into our solutions. So my observation, performance simulation is mathematically rigorous and represents a profound departure from traditional calculation approaches. Now, I want to emphasize this. I'm talking today about performance simulation, not about performance calculation. I'm going to explain in the next slide what's the difference. And I'm not interested today in talking about simplified calculations or steady state methods or pseudo steady state methods or regression methods or anything like that. I'm talking about simulation of the energy system. So these are the attributes of all energy systems which need to be included in our energy model. And if we don't include them, then do not please call it a simulation program. Call it a simplified program, call it what you like, but do not call it building simulation. The first characteristic we need to preserve is derives from the understanding that all energy processes are dynamic. There's nothing in a building or in an energy system or in a local community that's not changing across time. And they're all changing at different rates. So it's a complicated dynamic problem where we have to be concerned about continuity, mass balance, momentum balance, energy balance. And inside a simulation program, you will see equation structures like these, partial differential equations, which are tracking the energy balances with numerical methods to solve them. So no way are you doing an algebraic calculation unless it's somehow a very clever proxy for a dynamic process. The second thing we need to understand is that energy systems are non-linear. What that means is all the parameters of the problem change as a function of temperature or moisture content. In short, they change as a function of time. So we can't give a program a U value. We can't even give a program a K value or a solar gain factor, or we can't give a program a heat pump coefficient of performance. We can't give a program defined occupancy heat gains, because that's a linear process where we say we know the answer and we'll give you it to do a calculation. In simulation, we need to have models which are able to calculate the parameters required to solve the energy balances, and they can change across time. If a user wants to stop them changing across time, i.e. linearize the problem parameters, that's fine, but that's you reducing the order of the simulation program, and it needs to be declared so that people can understand the validity of the results. The third thing we have to encapsulate in simulation is the fact that all problems are systemic, that we're talking about lots of things that must be held in some kind of balance. We can't optimize for all of these things, but we certainly can hold them in some kind of balance by accepting a degree of trade-off. So we can get our capital and running costs okay. We can look at our thermal, visual, and acoustic comfort. We can look at if we're low energy. We can look at air quality and environmental emissions. We can look at impact on power quality and network interactions. We can look at how well we're demand to supply matching. We can look at how easy it is to control the system and what will happen if it's not got good resilience. So the models have to have knowledge of these very important performance parameters. And finally, all energy systems are subjected to stochastic influences. The most obvious one is weather. It changes. And so what's the point of taking a simplified program and doing an annual energy calculation, or even taking a simulation program, fixing its parameters and doing an annual calculation? Because weather changes every year. It changes across the life cycle. Also, equipment fails. So when we're simulating, we need ways of saying what happens if this chiller goes down? What happens if this solar control blind sticks and ceases operating? And finally, occupant behavior is stochastic. It's random. So we can't just say we have two people, each at 95 watts, and they're in from 11 in the morning till 3 in the afternoon. That's giving the program the answer. And that's not even what's going to happen in the real world. So we need to have inside our programs, not just these kinds of models, but also models of occupant behavior. So performance simulation must respect the thermodynamic integrity of the systems we're trying to design. And they must target reality emulation to confirm operational resilience. We're not trying to calculate something like the CO2 emissions against these standard assumptions. That has no meaning. What we have to do is calculate lots of things changing dynamically, and then take the results back in order to understand if we have a good design or not. So here's a little issue about dynamics and non-linearity. So there's a gas boiler, there's a fuel cell, there's photovoltaics, get my pointer back. There's a gas boiler, fuel cell, photovoltaics, wind turbine, gas turbine, heat pump, and all their characteristics are non-linear. So the performance, the COP, the efficiency, whatever we're talking about, the heat to power ratio, varies as a function of the context, which is changing with time. And that's also true of basic things like material properties. There's the variation in material conductivity with moisture content, and permeability changes. So the programs have to have models, models of heat pumps, for principal models, gas turbines. We don't type in a TOP for a heat pump. That's you giving the answer to the simulation program so it can do some kind of calculations. Neither do we just fix thermophysical properties. They must vary as a function of what's happening in the simulation. So performance simulation should provide these characterizations as outputs. These are outputs from the simulation. They're not required as optimistic input values. If you want to use a simulation program and you say, I am going to fix the COP, you can do that. But you've then got to declare to the world when they see the results that you've fixed the COP, and the results are only true for that. But a simulation program should not require you to input optimistic values. It should tell you how these systems will actually operate in practice and what efficiencies you'll achieve. The performance simulation approach, just quickly, is to take plant, buildings, flow paths, ventilation systems, electricity networks, and to divide them all up into small parts, and then to form for each of these small parts that represent the plant, cooling coil, the heating coil, the fan, the ducting, the building, the spaces, the air movements in ventilation systems and in air spaces, the electricity flow through electricity generators and also electricity sinks and interactions with the building. So we take all these parts and we form conservation statements, as the previous slide, conservation of mass, momentum, and energy. And we do that representing where there are conductive paths, convective paths, advective paths, where there's shortwave radiation coming in, where there's long-wave radiation exchanges, where there's electricity flows in and out, where there's contaminant sources, sinks, and we impose control on that. And we then have lots and lots of equations, and we can solve them simultaneously and move through time in that way. So performance simulation programs, all the big simulation programs, use these numerical methods. And many of them, some of them, not many, have inbuilt validation techniques. So in other words, they validate themselves. They do their own calibration of their models. They invoke parameter uncertainty procedures. And they allow you to vary the resolution of the model. So that's the state of the art. And not all models do that. Some simulation models are very poor in these regards. But the more evolved simulation models do have inbuilt validation, model calibration, uncertainty analysis, and variable resolution capabilities, fairly automated. So the merits of this approach are many. The approach encapsulates everything we're trying to do. It's got all the building physics, the thermal fluid flows, heat and mass transfers, all the radiant exchanges, all the plant system processes, electrical power flows, all the microclimates, all the uncertainty associated with renewables, control system responses, innovative materials, occupant behavior. It encapsulates all of that, and it addresses all the relevant issues: life cycle operation, human comfort, operational resilience, and so on. So performance simulation, it links energy, environment, human well-being, and design productivity. And that's obviously what we want for our industry. If they can use tools like this, then for the first time, they've got the ability to link these four important things and stress test at design stage. And this can either be done through an integrated program. So all my career, I've always been operating and trying to develop an integrated approach to this. So a single program that can accommodate all of this. Or it can be done by using cooperative programs, a program for lighting, a program for acoustics, a program for a HVAC plant, and somehow making sure that their outputs are from one are fed to the other, and then the output from that's fed back, and you can therefore cycle round like that. So whether you do it integrated or through cooperating programs doesn't matter, as long as you're encapsulating these issues. So my observation here is that performance simulation requires high resolution, feature-rich input models and standardized performance assessment procedures. What this means is the models are very high resolution once they're made. They have lots and lots of detail. They have lots of features in their models, and because performance assessment is standardized, the user doesn't have to do the performance assessment. They simply just have to ask the program to undertake the assessment on their behalf, because the performance assessments are already defined inside the programs. You can run them manually if you want, but that's a crazy way forward given the complexity of the problem. So here's a high resolution model. So in terms of, for example, dwellings, we would want to formulate a model, however we do it, which has full three-dimensional geometry. So we would have 3D geometry. We would have all the furnishings and artifacts inside the model would be there. We would have any renewables. We would have the boiler, if it was a central heating system. We'd also have a CFD model active inside the boiler, because we would want to look at combustion processes. We would also enhance the model, so we would have very, very many finite volumes at corners and at window frames, so we could look at thermal bridging and condensation. The electrical network would be represented in the model. All the heating controls would be explicitly in the model. You would see where the thermostat is. You would see how the thermostat, where its signals were going. You would have all your network air and computational fluid dynamics airflow models would be imposed on this. Not shown here, it's too complicated. So these would be high resolution models representing dwelling archetypes or specific dwellings. So either there's a library of archetypes, so you could have a semi-detached, a high-rise, flats, or you could adapt them to be your particular case. It's also possible to automate the creation of high-resolution models for whole cities. So this is the city of Glasgow, and we've automated the creation of models which represent various dwellings within in the city. So there are procedures where you can make fairly high-resolution models for large parts or whole cities, which then designers can come along and go in, take away the models they want, and then form the community to do their design simulations in order to progress the world. So performance simulation programs should, and many do, provide exemplar models. And they can be used as a starter in a new build or upgrade project. These models typically cover lots of individual archetypes. So my question would be, do we have enough typical models for use with this kind of simulation in Turkey? Could the Turkish organizations start to generate these high-resolution models as a resource base for the industry, with the industry helping, of course? How do we make high-resolution models? Well, it's not easy because we don't have a fully binned built environment where we can just go in and take a digital model out. So we need to have 3D geometry. We need to know the hydrothermal properties of all the construction materials. We need to know where there are thermal bridges and air leakage. We need to know all the internal thermal mass. We need to know the operation, occupancy, the lighting, and so on. We need to know all the technical systems for heating and ventilation. We need all the renewable components, and we need weather. And Where do we get such information? I think I'm losing a little bit off the bottom of my screen here, but not to worry. So normally, if we're making a high resolution model, the local authority, for example, if it's an existing building, might have construction drawings. We might have to do a site survey. We might go and get manufacturers' data for things like materials. We might look at building standards. And increasingly in the future, we will have partial BIM models, which already exist in a database. We can also grab point cloud models using modern technology for digitizing parts of cities. So there are a number of data sources we can consult in order to bring together these kind of data types in order to make high resolution models of parts of our cities. And that work is well underway in many parts of the world. These are called city cadastres. If we have such a model, then the outcomes from it address real issues, not made up issues like, what's the overheating in next July, but real issues like glare and daylighting utilization. We can see the glare across time. These could be animated. We can see the utilization of daylight, or we might go in and look at thermal bridging. So we can see how the thermal bridge is causing a problem. We can go adapt that part of the model until we eliminate this thermal bridge. This is showing mold growth predictions. So we can say, well, that's very bad, this level of mold growth here. And so what we'll do, this particular mold F, Stratibotus atra, is a very dangerous one. So we need to eliminate these. So we change something until that disappears. Mean age of air, looking at air freshness, and that's to do with well-being. Control dynamics, looking at the boiler cycle, the dynamic control of it, looking at the combustion processes, changing the excess air in order to get better clean combustion, and similar with in future with hydrogen processes and so on. Hydrogen consumption and power quality. So looking at voltage variation on a local area network, or looking at the import and export of power to a local substation, which is going to become huge with EV charging and so on. So performance simulation programs should make industry-agreed performance criteria and operational benchmarks explicit. So some of the programs now say, these are the criteria we use, we make them explicit, and the benchmarks of what's good and what's not good are explicitly stated and can be changed by the user, of course. So the user doesn't have to specify these. High resolution commercial models, same thing. We can make, this is a big construction company in south of Paris. So we can make high resolution models that can all be gridded up to get all the CFD and for air movement. All the control systems can be added in, the lighting systems, the HVAC systems, all the electrical networks are added in, the occupant behavior. So we can make high resolution models of commercial buildings, and there's nothing you cannot ask a model like that about performance or how to improve performance once you have the high-res model. So, and the performance outcomes, the kind of benchmarks, if we think, is that okay? So you give the high-resolution model to the program, the program goes off, and it does its simulations. So these are some of the simulation outputs. And it looks to see whether it's compliant with ISO 7730, predicted mean volt, draft risk, vertical air temperature, stratification, floor temperature, radiant asymmetry, comfort. In terms of glare and lighting, trying to comply with that standard. It looks at glare relating to light sources, uses particular criteria, UGR, Unified Glare Rating, and then it comes back and tells you whether you would be compliant with that. And in terms of air quality, it will look around over time and tell you when you will be compliant with this standard and when you will not be compliant with that standard, and how often you will break it. So these things are automated now in simulation, or at least in whatever simulation program you're intending to use. You should ask the vendor to make sure these things are automated, or you've got the ability to define the procedure yourself and then save it as a script for later. So these standard assessments, you must expect them to be in the programs in future, so that they can be automatically invoked, rather than allowing every single human being that wants to use a performance simulation tool having to go through and say, do a simulation over this month, hold the temperatures, set points at this, take the output, add it all up, and so on. It's just nonsense, and we must stop it to move forward to get the real prize of this technology. And that needs to come from your Turkish institutions and your leading industry players getting together with your academic base and pushing forward to something that really could be quite a change. And I have to say, IBIPSA Turkey is in just as good a position to achieve these aims as any other IBIPSA region. If you start going for it now, you could be leading. So there's just an example of how we've codified in our program the UK regulations. I won't go through it, but there's a SIBS-E criteria for offices. And so the program is simulating time step simulation over multiple years as the building is put through its life cycle. And it's tracking all these things and saying how often they comply, how often they don't comply, and giving a comprehensive report at the end to the design team. And so what we're looking to do is to produce a holistic insight into performance, not taking out tons of CO2 or kilowatt hours of energy consumed or capacity of renewables deployed, but rather we're trying to put together integrated views of performance where we can see our plant capacities, our thermal comfort, our visual comfort, our daylight utilization, our acoustic comfort, our emissions strands, our winter behavior, typical spring, our annual performance. You can put anything you like on these integrated performance views, and they become the currency of debate when talking to clients. We've managed to improve this characteristic of the building, but it's cost us just a little bit more energy, but we think that's acceptable, and so on. You have a dialogue. You cannot optimize everything. So these outputs need to be made explicit so we can see the trade-offs as being explicit. And then we can say project proposal 1, this is the IP, the integrated performance view. So we'll change something. Here's the integrated performance view for proposal 2. Slightly better, but not good enough. And you keep going until it's good enough. Of course, all the outputs from simulation these days are, the word is experiential. You don't give numbers to people. You let them see how the voltage is varying at the local transformer in the substation because of power flow in and out, and when you're going out with the regulation limits, which you will not be allowed to do. You can see the distribution of air in the large space with all the properties of air, or fresh air coming in and how old is the air in the space as it circulates. How much, if we use daylight, how much is that daylight, the blue, displacing the electrical light, the red? You can see the glare. You can see the illuminance distribution, which is raw energy. You can apply this internally or externally. You can see the street scheme. You can control the lights to reduce them to save energy without affecting people's safety. You can see critical environmental conditions. You can see what happens if a fire starts, whether the mechanical ventilation system would be able to come on as an emergency measure to extract the smoke away in a certain way away from the exits. We can go into detail and look at the thermal bridging, the mold and problems with moisture in buildings. We can look at the external environmental emissions and the low voltage networks. So you can appreciate, you can almost feel the performance rather than just being given lots of numbers. And that's the best way to communicate complex issues to different stakeholders, whether they be your client or the public at large or regulatory bodies. You can communicate how your design will work. So the observation, while performance simulation is potentially better, potentially quicker, potentially cheaper than traditional methods, its effective application will ultimately require a change in business work practice. You can't just take this into a business and expect just somebody in the corner to run it. You have to change the way you make the models, calibrate the models, send them for performance assessment, get back the integrated views of performance, convene the team meeting to discuss whether the trade-offs are all right. That has to be keeping your own exemplar models so that you can have a fast start the next time there's a project starts. You need to change your work practice to a degree. And you need to train staff. You can also embed this simulation technique inside simplified tools. These are some examples that my group's been playing around with. Our program, which is called ESPR, is embedded in a GIS tool that's used by Glasgow City Council to look for renewable deployment potentials in the city. So they don't know there's simulation behind this. They simply go in and use a GIS tool and click on spaces and click on menus, and behind the scenes, the simulations run. This is a stock upgrade planning tool. We've put the entire Scottish housing stock behind this interface. And the entire Scottish housing stock was pre-simulated with advanced simulation. So people can come in and simply play tunes on this. They can say, if I was to introduce this insulation standard, what would happen? If I was to deploy these renewables, what would happen? And they get the answers instantaneously because the simulations are already embedded behind it. Same for the performance rating of buildings. We've made little tools which rate them based on simulation models. This is upgrade quality. So Glasgow City Council, when they're doing a big upgrade of maybe say 500 houses, they make a high resolution model of 2 or 3 archetypes. That model informs this tool what to expect, and then the tool says whether they're realizing their potential after the upgrade takes place. Control system design, very specific, biomass heating. So you can put simulation behind simplified interfaces to be easy to use applications, which are then just single focus. So next generation modelers, this is what they'll need to be trained to be able to do. They'll need to be able to establish a model for some unconstrained base case design. I don't have time to go into this in detail, but just feel what I'm saying. So they're going to have to so you make a model which has got not too many things in it, a base model. You calibrate the model using some reliable techniques. Many of these are built into the programs now. You assign boundary conditions of appropriate severity. Much of this is now inherent in the program. You undertake integrated simulations, and many of these are automated within simulation programs. You express the performance of all your parts in terms of suitable criteria, and many programs define these criteria for you. You then look to see where you have problem areas in terms of if these criteria are acceptable or not. You then analyze the results to identify the cause of the problem. So you go into the engine of the simulator, you say, oh, what's causing that criteria to not be good? So you find the cause of it, you postulate a remedy, you then establish a revised model and repeat this circle. So you need a performance assessment manager in your practice who is able to ask someone to make a model because they've got good architectural skills and they're good at using CAD to make models. Maybe an engineer who can add in the CFD definition with approaches, and then you need to develop this approach depending what it is you do in your business. Are you talking about net zero design or hybrid systems design or EV integration? So you set these up. So undergraduate, postgraduate, and continuing professional development courses should align to this need and help people to understand how to do this. So when they come out into business, we have a much richer environment than we have at the moment. The approach is generally applicable. We can apply it to smart street lighting, car park, EVs. This is a simulation model with our program. We've got PV in the roof and we're simulating all the battery charging and EV charging and stochastic this and that. Translations to the grid, city opportunity mapping. We've even used it to do, this was a virtual test chamber for the Fiat car company where they could drive their cars through a simulation program, looking at what would happen in fog and collision avoidance. Microgrid design, great for that. Internet-enabled energy services, great for that. Urban energy management, so we can embed simulation in all of these. And this computational approach to design, all this says here is if you start with your design team, and you have a little look at the program. This is, you're running some program, some performance assessment program that you like and you trust, and it does these things. So you've got your team sitting in there, and they look at some databases and they get an idea of what materials to use. They add in the geometry, they add in some surface properties, they add in some details, they add in some boundary conditions like the sky. They then look at where there's glare and so on, and daylight utilization. Add in a control system. You can then start to see displacement of electricity. Add in your, look at your ventilation systems. Look at your HVAC systems. Look at your embedded renewables. Look at your critical indoor environmental conditions. Integrating all these things. Looking at smart grids and so on. So as you put a little effort in up here, you do your CAD bit and you get some pretty pictures out, you get a reward. And maybe you could talk to the client about how you're going to plan an atrium in order to get daylight, to not use electricity as much in the offices beneath. If you get the go ahead, you then start to add in more detail. Here we're adding in, a sky, and we're doing that critical glare avoidance in the offices with that atrium. But we're also looking at the daylight available. So we can put a photocell in and start to switch the lights. So as you put more effort into defining the high resolution model, so you get more of a reward. You get something you can talk to your client about and move the design forward. So the performance simulation approach supports a digital twin approach. And CAD tools are evolving to include technical systems and their performance returns. And so are BIM models defining these properties. So future CAD will be all the things that we've seen before. So we see all the enough to enable, this is Bentley, to produce that. But you cannot do building performance simulation with that model because it doesn't have context or operation or occupants or materials or flow or HVAC or renewable. It doesn't have these things. It doesn't have standard performance assessment procedures. So these have to be added to the CAD environment. So performance simulation defines the superset of data that needs to go into the BIM models, although CAD should provide the control of the application process. So we need to extend BIM to cover all performance domains and there are people working on that, and to incorporate all process models for standard performance assessment. So this is a picture into the not too distant future. Simulation programs at the moment have all of these data sets, these models, but BIM is moving towards encapsulating that, which will mean we can all use the same models in future. Business integration needs then. You'll need to have program validation techniques. As I said, they're inside the programs. You'll need to have some support in Turkey, this is, for tool selection. So a company goes along to IBIPSA Turkey and says, what program should I use? Well, IBIPSA Turkey needs to be able to say, well, we wouldn't recommend this one because frankly, it's not very good for your purposes. And this one over here is pretty good for your purposes, but it's not able to do this yet. We need a place of we can go to do that. We need a place to go for user training. The university should be doing more of this, if not the industry itself. We need to be able to accredit users and tools, and that's a role for IBIPSA to say that, you know, this user has gone through training, is now an accredited simulation tool user. We need to extend BIM to other domains. We need to help people understand how you abstract real big complex projects to the essence that's required for the simulation programs, so you're not simulating everything when you make your the whole city when you make the high resolution models. Calibration procedures are usually inside the model, but you need to understand how to use them. Quality assurance, you need to understand how to coordinate the tool, although that's getting easier because a lot of this is automated. And if you're using multiple tools, how to interoperate them. And then there's all the issues about designs change across time, so you need to look back and update the model. You need to develop your scenarios in order to test the robustness of your design, and so on. You can read this now or later. So industry should dictate future program functionality and support structures. It's the industry that needs to demand these things. And until the industry demands them, they will not exist in a good form. And we're having a terrible time throughout the world getting the industry to go to its academic base and its government support base and demand that these tools have better functionality as they need. And then things would move rather quickly. At the moment, it's academic push rather than industry pull. So professional bodies should provide standards for design representation and performance appraisal. And they should resolve the dilemma between the secret programs that you can't see inside and the open source programs, so that the industry can use open source programs or proprietary programs and mix the results in a confident manner. So performance simulation is evolving to deliver reality emulation as a service for the resilience testing of proposals and become a source of digital models for off-site manufacturing. So this is an environment that exists. You define a model, you upload it to a cloud server, it adds in all the CFD definitions and does the model calibrations automatically, initiates perpetual annual simulations, looking at all these things, automates all the results probing as the simulations take place, suspends the process where performance is deemed unacceptable and lets you adapt the design, and issues a compliance certificate on successful completion. An automated cloud environment. Maybe the cloud environment is operated by a new company in future, and maybe other companies upload their models to that and pay for a standard approach to be applied. So when you get your compliance certificate, it's understood to be a good design by everyone. So we need to move away from licensing a program, buying a program, to buying a service based on approved tools. So that environment has lots of design, lots of tests of increased stringency. So a basic test, an intermediate test, an advanced test for the domestic market, current regulations, passive house standard, net zero standard, non-domestic, current regulations, naturally ventilated, integrated systems, community level, integrated renewables, district heating, hybrid smart control, single building, community scale, AI-based. So these are all procedures that are predefined and put in the resilience testing environment that everyone can then use and have a standard procedure. Just finishing now, if we have a high resolution model like this, then we can send it to that simulator in order to confirm. Let's say we wanted to upgrade houses in Ankara. So we make models like this, high resolution, of some of the archetypes, some of the houses. We send them to the simulator and we confirm that the upgrade we're going to apply, here we're going to put a new facade, a new gable end, we're going to put a new roof with integrated photovoltaic panels on, we're going to put advanced glazing in, and that's the upgrade. We've got that model with the upgrade sent to the simulator, confirming that the upgrade will work. We can then take that model and we can take parts of that model. Here we're taking just the facade out in different digital formats, JT format, IFC format, STL, and so on. And we can send those parts models, that's an anchor, which is anchoring this facade to the old building. This is the smart window frame. And we can send these in any format into the factory for off-site package production. So these model parts get sent in to the factory where the robots and the various processes, the flat evacuation bed and so on, the nailing gun, the insulation spray, all of that is programmed against this model, which has been proven to be a good idea for the upgrade. And then the parts arrive on site and there's on-site application. So the high resolution model that we're starting to make for performance simulation, they can feed off-site upgrade package manufacturers as a means to upscale building refurbishment. There's a project in Europe just now, it's called In the Zero, and it's using this approach. My team's doing this part of the project so that we are making high resolution models of people's estates, and then that's going right through to the factory, and we're proving that then we can deliver the components on site. So you can go from a few hundred upgrades in a year to tens of thousands of upgrades in a year based on putting the effort up front in your performance simulation. So in conclusions, if we want to address the real energy-related agendas, then we're going to have to develop simulation tools that can accommodate the explosion of options that we're seeing. True simulation respects the system integrity in relation to dynamics, non-linearity, all the part interactions, and all the stochastic influences. The technology is a little way to go before it's easy to access, appropriately aligned with reality, and unambiguous, and delivers outcomes that are readily understood by everyone. But let's say it's got a little way to go. It's come a long way, and a lot of these things have been automated already in some of the programs. And as the industry keeps pushing for that, and the agencies that support industry develop definitions more that can be automated, then I think this will move ahead very rapidly. The focus of practice needs to change, however, from design calculation. Stop calculating things to life cycle performance assessment and testing the resilience of a proposal. This is a terrible way to go about. At some point, you need to calculate the size of something, but only after you've put that thing into the model and it seemed to be resilient, then you can take that size out. But you don't do a heat loss calculation to get the size of the boiler and then think that's the problem solved and then move on to something else like lighting systems. Some questions remain relating to how do we stop treating computer programs as competing entities? My program's better than your program's not as good as that other one, and come into a more collaborative mode of working, understanding what's good about programs and joining them. Providing services as opposed to selling programs. Don't buy a license. get the program for nothing, but pay for the service in using it, because you send your model somewhere. Maybe you're the one selling the service. We need to standardize performance assessment procedures. We need to deliver all programs that automatically self-check their validity and their calibration. We need to get all the programs certified by independent agencies like IBIPSA Turkey, should be certifying the programs for use in Turkey. And we need to continue to extend BIM to support all aspects of integrated performance simulation, rather than just the CAD part that it does at the moment. I'm not going to go through this, but just for any researcher in the audience, the IBIPS has produced a white paper, and it has lots of propositions for the future, and I've touched on all of these at some point in my presentation. But these are formal propositions that IBIPSA will do this, IBIPSA will do that, IBIPSA will, and it's a lot of the things I've been saying. There's 9 propositions and another up to 16. And that's the reference for it in the IBIPSA journal, and you can see these propositions explained. And they are what IBIPSA regions, as well as IBIPSA Central, should be trying to develop initiatives in each of these to further these propositions. So thank you very much for your attention. I think I've finished just on time. I'll pass you back to Neşe, and I'm not sure if questions.
Yes, thank you. Thank you very much. It was really valuable. It was very useful for us. I think it was. We are very happy about listening you. And according to the question part, I can understand that the audience is very happy about listening you here. So thank you for everything.
I just wish I could speak Turkish.
Okay, but they can understand English. We can communicate.
I'm seeing all the questions, but I don't understand them.
Okay, there are questions. I will skip to the question part, but I would like to remind the attendees that they can write their questions to the question part. If you have any, please add them here. There are some questions. For example, I will start with this because I'm an architect. What is your suggestion for architects? How should architects adapt to rapidly changing technology and computer programs? And for engineers, writing the software of a program should be easier than learning the program itself, says Nilay Özeler. The question is related with that.
Let me answer the architect one. I have a research group, and there's maybe about 25 people in the research group, and I have 3 architects, and they are the best modelers. My architect researchers are the best. There's something about an architectural education that gives you real insight into complexity and parts and how they come together. And usually good architects have good digital skills. So my best modelers are architect trained. So that was the first thing I'd say. That's not to say I don't have good engineers who are good models, but architects particularly, I always would employ a good young architect. The other thing is, I don't believe that every architect or engineer, for that matter, should be running these programs. I think these programs should be somewhere else with people looking after them. And what you should be doing is saying, here's what I propose. Would you evaluate that for me, please? And we must move towards that service culture. So you don't run programs. You don't have to learn how to run a program. That's automated already. That's the easy part. You only have to learn how to ask the right questions and generate the correct design hypothesis. Understand the results you get and change your design hypothesis. And that's what all engineers, architects are trained to do. As for coding, I think there's nothing more exciting in this world for a young person to sit down and use a high-level language to code something. but you will never code what I am talking about. This is hundreds of years, hundreds of person years of effort to get to these programs. All you can do is add a new module into them, perhaps, or create a new script to use them. But to start to create your own computer program for building performance simulation is madness. Because by the time you do that, you'll be retired and you won't have made you won't have evolved the state of the art. So I'm afraid the state of the art is so progressed now that you really have to, but you can download the source code of these systems and then go inside them and code and add things in. And indeed, that's a very, very powerful way if a smart young person can go inside a simulation program and change it. I'll stop there.
Okay, thank you very much. Another question from Levent Koçalioğlu. He told that existing buildings has also very importance about energy efficiency. So do you think that building energy modeling and simulation can play a role to improve energy efficiency of existing building stock?
Existing buildings are the most important part, and that's what building simulation was designed to do. Building simulation loves existing buildings. You can make the models easier because they're existing, you can see them, you can measure them, so the model making process is easy. You can calibrate them easy, the models, because you can make some very simple measurements to make sure your model's well calibrated. And you can simulate all various options for change and then tell the local authority or tell your client which is the best upgrade strategy. So I would say the raison d'etre, the reason for being of building simulation is for application to existing buildings. Yes, new buildings too, but new buildings are the least of our problem. Existing buildings is the big challenge.
Okay, thank you very much. And another question from Ayşegül Terci. There are many questions related to the future of the simulation, actually. You mentioned some key points, but there are some new questions. What do you think about the next? What do you think that what is the next for the digital twins technology? And maybe I can match it with another one. Maybe you can answer together. How do you see the future of energy modeling? Will the data or artificial intelligence-driven models be able to surpass the physical modeling approach?
But by physical modeling, does that mean making an actual scale model? What do you mean by physical modeling?
We can.
You would know. You would know the answer to that.
Dynamic modeling. The answer was dynamic modeling.
Right. What I've been saying today is that the building performance simulation has been on an evolutionary trajectory. It's been evolving, and it's been going in a certain direction. We can see where it's going to go now. We know where it's going. So I know I can't predict the future, but I can say roughly where we're going to go. We're going to have BIM definitions. So the BIM standard is going to evolve so that it covers all the aspects required for building performance simulation that I mentioned in my presentation. So it won't just be the form and fabric. It will be the technical systems. It will be the occupants. It will be the control systems. All of that will all be part of the BIM model. There are, throughout the world, teams, research teams, making what I call city cadastrals, so city models. These are digital models of what's already in our cities. So a lot of that already will exist, and so we'll be able to pick it up. The simulations themselves are becoming more highly functional, so that they simulate the heat, the mass transfers, the momentum transfers, the people movements. Everything is simulated in these programs, and they're simulated at small time steps. So we're emulating reality. The simulation process is following what would probably happen to the building in reality. So we can just probe those reality results and say, oh, I don't like that. Well, that's pretty good. And so we can begin to see if the building is resilient rather than try to calculate a performance state. We're just saying, well, it's operating quite well. I quite like that indoor environment. We've got a little problem over here. I'll look at that later. So the simulation is doing that rather than just calculating something for you. And also the simulations are moving on to cloud space. So they're moving out of download a program, put it on your PC or your laptop and run it yourself, to rather use tools to make models and then send them to some place. It might be a server in your own organization, which has already got, you know, all the definitions of all the simulations inside your. If it's a big company, you'd probably have a server inside your company. But you want to have people sitting on, you know, like I'm sitting just now with a laptop and a screen. You know, individuals doing simulations. That's not what's going to happen. The only thing I'm not sure about is I am very saddened by the lack of industry pull. Until now, everything IBIPSA represents is academic push. And the functionality is great. It's getting better all the time. But there's not a lot of industry pull for lots of reasons. I like my industry. The construction industry is a great industry. I'm not criticizing it, but it's not pulling this technology into its work practice on its own terms yet. I don't think it has the vocabulary. It doesn't have the structures that maybe IBIPSA Turkey can bring in Turkey, so they can see the issues and say, yes, we really want to move this way. And that's the only sad bit I have about the future. That future is very slow, and it won't come until maybe it'll accelerate once one of the IBIPSA regions starts to really get its industry, you know, pushing for this technology and young people coming out with the skills.
Okay, thank you very much. There are many messages thanking to you. They thank you for your presentation, for this comprehensive presentation. There are many messages like that in the questions part. I would like to also tell them to you. And there are some questions related to the softwares. If you suggest this software or if you suggest the other one, what do you think about this software? There are many questions related to that. So I would like to ask, there are many different softwares on the sector, and now many people are using them. There are many users. So how do you see the sector now, and what is your opinion about that?
Right, I'm not going to be drawn into saying program A is better than program B. So I have my own view on what programs are good and what programs are not good, but I'm not going to, in an open forum, start to criticize or compliment any program. What I will say is there are some, IBIPSA itself has a big directory of all the programs in the area. So that's the first port of call, to go to the IBIPSA tools directory, and you can see all the programs listed. But that itself doesn't tell you what program to use. Then you need to use IBIPSA connections to ask questions like, I've got this problem, is this program good for that? But what I will say is all the programs are partial. None of them are perfect. So that you may have a program that's great for doing lighting simulation, but it can't do all the other things. Or a program that does quite a number of different performance assessments, but some of them are steady state calculations, and I don't know what that means because there's no such thing as steady state. So you'll always find that there are programs which have got deficiencies, which are not as good as they should be, but they've maybe got a characteristic that really is good for you. And that's where I would suggest you might want to use a number of programs. So you use program A for this purpose, and then program B for another purpose. Even although program A says it can handle that, you don't trust it, so don't use it. My background is more in academia, and I write integrated software that covers all of this stuff. But that's not necessarily easy to use. And that's why we're going the route of putting it on cloud servers and automating it. But you can, anyone who wants in Turkey can download our entire source code of the ESPR system in this case. And that does all the things I'm talking about today. But I'm not suggesting that a company should just download it and within a week would be using ESPR to do commercial things. I think that would need to be something a program like that, and other programs in the world that are like that, maybe should be supported more by bits of Turkey, so that the collective knowledge allows it to be well applied, rather than taking a big complex program and some individual being told by some line manager that they've got to go and do some simulations. It doesn't work like that. So I think there are many programs. There's the BIPSA directory, and then there's your own good office that can inform your participants here about what programs might be fit for purpose. And anyone who wants can email me directly and ask me a personal question, and I will give a personal answer. But I don't want to choose programs open air like this.
Okay, sure. There's another question from Engin Şeker. As energy modeler, I was struggling with exporting energy modeling database to another energy analysis program to complete simulation. Because some programs are not sufficient for full analysis mode, this process may take much time and we may face lots of problems during integration. Will you think that there may chance to achieve common and interchangeable file types for all energy modeling programs in the future?
The answer is absolutely yes, but I'm not sure when that future will be. There's the BIM standard and it evolves. And we will come to a point in the future where the data entities in the BIM standard will correspond to the requirements of performance simulation. When that day comes, all programs will be able to use the same input model. I only ever work with my program, which I know its input model. And we write converters if we want to send data to other programs. But I feel for your colleague who asked the question. It's a very difficult issue, and it normally requires a young man or woman who's quite skilled to take the data model from one program, manipulate it a little, and then send it to another. And it can be very time consuming because the programs are all developed by different people at different times. And the BIM standard is not good enough yet for building performance simulation.
Yes, it's a big problem, I think. And there's the last question is related to the operational part. Is the ideal digital energy model, according to the SIPS, applicable in the construction site, or the ideal model was changed by a manufacturer in the construction site? And it is related with the second question. Have you any comparison experience after the finishing all the installation in the building site for a digital model and the real model, like comparison? What are the main problems after on-site inspections?
Well, what happened in the past, organizations in the world have developed validation tests. And these validation tests were based on empirical data. So they would monitor buildings, and they would get real data, and they'd make validation tests. And then programs like the one I develop and other programs in the BIPSA family, they can use these tests to make sure that their programs are valid. That's the past. In recent years, with the advent of Internet of Things, there's lots of small devices that you can put into buildings. If it's an existing building, which can monitor the state of the building. And in the big European Hit-to-Gap project, which we were involved in, we put these small sensors into buildings in order to capture enough information to automatically calibrate the computer program model that you're making. So somebody's making a model, and you give the model to the system, and it automatically changes some of the parameters by automatically calibrating it against measurements. So that's where we are at the moment. That will then in the future go even further, because all buildings will be AI'd. There will be lots of devices, and we'll know how they're performing, and you'll be able to see what the predictions were and see whether they align with reality or not, and adapt. And that's very important for the future. So I didn't really catch the first part of your question, but this issue of closing the loop between the predictions and what then transpires in the real world is key going forward. And we must expose, so no one can tell any lies, make predictions, and then you never know if they come true or not. What you have to do is close that loop to make sure that what we design actually did work the way we thought it would work. And if not, why not? So we can evolve the models further. When I was very young, I'll just say this, my professor told me that the destiny of all this computer modeling stuff was to enable participatory democracy. That means that everybody in the design team, including the clients, would be able to say, what happens if we do this? And then we get the result right away. And that has always been in my mind since I started it out as a researcher. And every development I make, I always think, one day, participatory democracy in design. It's not just an architect telling me that's the answer, but it's everybody can get together around the model and can see how it's likely to work. Is it resilient? Is it going to be easy to run? Is it going to be good running costs? Is it going to be good indoor air quality? All the things, people are interested in different things, and they'll be able to see that from the model. And then as the design actually works in practice, there'll be a monitoring program to make, and monitoring won't be a research team monitoring. It'll just be automated as part of the construction process. And that's maybe in the fullness of time. However, perhaps for the next 20 years, there'll be no modeling if the industry doesn't pick it up, because the industry might want to download a simple steady state program, run it against a compliance check, tick 3 boxes, and then build a building. If that's what they want to do, then fine, but then we need to attack the industry if they're doing that, saying you're not building things that work well, because you're just doing tick box. But I'm afraid that might be, because the industry is about money, it's about, you've got deadlines and clients and budgets. So I'm not sure when this revolution will come, where we can use these simulation tools in this wonderful way that I'm talking about. We shall see. It's your generation that needs to make it happen, not mine. It's your challenge.
We will try.
Yeah.
Okay, it's a hard challenge. Yes, I think the questions are like this, and so I would like to ask your last words about the webinar and I don't know, last words to us maybe.
Well, it's a real pleasure to talk to all my colleagues in Turkey.
It was our pleasure. We are really happy about it.
Be able to travel there physically and enjoy the delights of Turkey. And I would just say that I guess my slides will be available to all your listeners, so that they're very welcome to have the slide pack. And they should email me. My email's on the first slide, and they can email me any question they want. If I have 100 very long questions, it might take me ages to answer them, but I'll try to answer. They just email me short questions. I'm very happy to answer. And I'd like to wish you all good luck, whatever your walk of life is, whatever your purpose is. Good luck with what you do. And if you can take simulation technology on in a way that benefits humankind, then wow, I'm happy.
Okay, so, thank you very much. Thank you very much for your good wishes and for your presentation. Provide us very wide view about the building performance simulation, I think. So I would like to thank you again on behalf of all of the audience and IBIPSA Turkey.
Goodbye then.
Goodbye.